Hi guys, this is Joe. In this video, we're going to be looking at hypothesis testing in statistics. We're going to be looking at particularly the p-value testing here. So first things first, what is hypothesis testing? Well, it's when we're testing a parameter and seeing whether it is valid or not. There are certain parameters that which everyone assumes to be correct, but there might be someone else who says this value is incorrect, and so they'll perform their own experiment, calculate their own p-value, and then they'll conclude certain characteristics or say whether it's incorrect or right. And so there's a way of testing this all out, or way of laying it all out. So first things first, we define what our x is, x being a test statistic. So we say let x equal to the number of something. It depends on the question, right? So it depends like what they're counting. And this we call the test statistic. And then because we're dealing with binomial, we're going to define our binomial distribution. And then we include or write down something called a H0. This is known as the null hypothesis. So this is the value of p that everyone assumes to be the correct value of p initially. Right now we have the H1, which is known as the alternative hypothesis. So this tells us about what the parameter is if H0 is shown to be incorrect, i.e. the null hypothesis is shown to be incorrect. So it could be that p is bigger than 0 or p is bigger than something or less than something, in which case it's known as a one-tailed test. If p is not equal to, in this scenario here, this is known as a two-tailed test. So this case just tells us that p is not equal to the original value that we all assume to be correct. We'll look at these two differences in more detail later on. Next, we have the significance level, sometimes known as the alpha, and this is the value of the percentage that the question will give you. It could be mostly 1%, 5%, 10%, and it just tells us how confident we are in our results. So for example, if the significance level is 10%, and then we get a result, we can say now we are 90% sure that our result is correct. It's very, very hard to get 100% sure, right? Because we're looking at a sample, and the sample itself might have some bias as well. Obviously, the smaller the significance level means we're more confident. So ideally, we want to prove that it's 99% confident with our results. Right, so how do we get to our results, whether we reject or not reject the initial null hypothesis? Well, I've drawn like this bell curve here, right? Where this middle line, let's just call this mean. So you can just imagine this bell curve as like the probability of a certain value occurring. So the mean value will have the highest value of occurring, right? And so as it goes further away from the mean, it's less likely to occur. That's how we get this bell shape here. And what I can deduce from this bell shape is label certain regions. Let's call this A and this region B. And these regions are known as the critical region, like here. And if our experiment lies within the critical region, then we will reject H0. Because it's, as you can see, imagine, it's very difficult to lie within the critical region, right? Because it's so far away from the mean. But if it does, it means, oh wait, there might be a problem with this p-value, and so it's likely to be rejected, i.e. the initial one likely might be wrong. And so that's what the critical region is. The way we find this critical region is using the significance level we found earlier, this A value, right? This alpha value is actually going to be imagined it to be the area of that region, okay? So the smaller the alpha value, the smaller the region will be, and therefore it's harder for it to reject it. But if we do manage to reject it, that's why we have a higher confidence in our results. So that's one way of finding or deducing whether we reject or not reject H0. Another way is actually using the probability. So we'll get a test statistic, we'll get a value we get from the experiment, and then we find the probability of that happening. If that probability lies within the critical region, i.e. is less than the alpha value, then we'll once again reject this H0. So there's actually two ways of doing it. You can either find the critical region, or you can find the probability of that event happening and then compare it with the alpha values. We'll look at both methods later on with an example. But once we find our probabilities and we know whether to reject or not, then we just write a conclusion. And in the exam, they just want a specific way for you guys to write it. So the first sentence should always be, there is sufficient or insufficient, it depends whether reject or not reject, evidence to reject H0. And then we write a line concluding it, but in the context of the question. So there might be the P is like the probability of disease happening. You have to write it in the context of that question. So it differs depending on the question type. Let's start off with a one-tailed test. So we have a polling organization claims that the support for a particular candidate is 35%. It is revealed that the candidate will pledge to support local charities if elected. The polling organization thinks that the level of support will go up as a result. It takes a new poll of 50 voters. Describe the test statistics. So first things first, we're going to say let x equal to something. So x is the number of. Now what we're testing, or what we're counting, the number of people who support the candidate. So that is going to be our test statistic. Now a null hypothesis, so our H0. H0 is the p-value that everyone assumes to be the correct value. And it says the original one is 35%, so 0.35. Okay. Now H1. H1 will tell us a p-value. It won't tell us a specific value, but it will tell us whether it's larger than 0.35 or less than 0.35. And this all depends upon the question. So there are a couple of words that you need to be aware of. So you need to find these words which says the polling organization thinks that the level of support will go up as a result. Okay. So if it goes up, it means the probability of it voting for the candidate will go up, meaning that P will be larger than 0.35. That is what a H1 is going to be. Now, it says, using a 5% level of significance, find the critical region for the test to check for the belief. Right, so what we're going to do is now, our alpha value, they said is 5%, so it's going to be 0.05. And so I'm going to draw a bell curve again. And now, we have to find the critical region. Now, the way we go about finding it is all dependent upon this H1. So you can see this H1 here is larger than 0.35. If it's larger than, the critical region will have to be on the right-hand side of this mean line here, okay? If this P was less than this 0.35, then you find the value in the bell curve. You will have to find the value which is less than here in this region here, okay? So it all depends upon this H1 value here. But we know that it's larger than 0.35, so it's going to the right. So I'm going to call this value A. And so this area has to be equal to or less than, I mean just less than, this alpha value here. So I can say that the probability that X is larger than or equal to some A value has to be less than 0.05. Okay, so this is how we're going to find this critical region. If it was, for example, if I was looking at this example here, let's call this one A, then the probability of X is less than or equal to A, because this is going to be less than, would also have to be less than 0.05. So the positioning doesn't affect whether it's bigger than or less than 0.05. It just depends if it's less than or equal to A or bigger than or equal to A. So in our case, we're bigger than or equal to A. So now I could go about rearranging it. So 1 minus probability that X is less than or equal to A minus 1. It's less than 0.05. So therefore, probability of X being less than or equal to A minus 1 has to be greater than 0.95. And remember from earlier, we have a binomial distribution, and N was how many? Well, they asked 50 people, and P is 0.35. And so what we can do is from the binomial distribution video series we looked at earlier, we can find what our A minus 1 is using the table or using the calculator. And its A minus 1 should be equal to 23, so therefore A is going to be equal to 24. If you guys are a bit confused about how we found this A minus 1 is 23, maybe go back to the binomial distribution video, and now it explains how to do it in that video there. Well, anyway, we found A is 24, meaning that the critical region is when X is larger than or equal to 24. So from out of 50 people they've asked, if we get the value of number of people who support the candidate as larger than 24, it means that we reject our H0. We found a critical region. Right. In C, it says, in the new poll, 28 people were found to support the candidate. Comment on this observation in the light of the critical region. So they found that 28 people supported it out of 50. 28 is larger than 24, which means that we reject H0. It is within the critical region. So if this is 24, right? So 28 is within there, so it's roughly here. So therefore we reject it. And so we can conclude now, so it says there is sufficient evidence to reject H0. And remember the last sentence was a conclusion in context of the question, right? So what were they theorizing? What they were saying that if they go to a charity, the probability or the percentage of people who support the candidate would increase, right? And that is correct, right? So we can say going to charity will increase the probability of support. Okay, so it's just answering or concluding in the context of the question. Right, let's try another one. So we have May commutes to work 5 days a week on a train. She does 2 journeys a day. Over a long period of time, she finds that the train is late 20% of the time. Over a new company that takes over the train service, May think that the service will be late more often. In the first week of the new service, the train is late 3 times. Okay, right, so first things first, let's write our test statistic X. So X is the number of, in this case, trains late, right? Okay, and we have x is binomially distributed. N is how many? Well, she does two, it's very important, she does 2 journeys a day, 5 days a week, so n will be 10 times. And the probability of being late is 20%, so 0.2, like this. Right, so H0, P is the original value, 0.2. H1, P is going to be something 0.2. So it defines a couple of key words here. And the important thing is, May thinks that the service will be late more often, okay, which means that the probability of being late will be greater, right? So in this case, our H1 is P is going to be greater than 0.2, like this. It's a one-tailed test, right? Now, you may assume that the number of times the train is late has a binomial distribution. Test the 5% level of significance, meaning our alpha value is 0.05. And test whether or not there's evidence that there's an increase in the number of trains being late. And out of 10, they found that 3 trains were late out of 10. Right, as I said earlier, there's 2 different ways of doing it, so I'm going to show you both ways. So let's use this critical region method. Critical region. So I'm going to draw my bell curve, like so. Okay, and then the region, as I said, it follows H1 and it says it's bigger than, right? So the region is going to lie here and call this A, and this area has to be the alpha value, which is 0.05. So I can say that the probability that x is larger than or equal to A has to be less than 0.05. Okay, so the same thing, we do 1 minus probability that x is less than or equal to A minus 1 is less than 0.05. So we're looking for a value, the first value, which is bigger than 0.95, like this. Okay, and it turns out that A minus 1 is 4, so therefore A is 5. So it says that the critical region X is going to be anything larger than or equal to 5. Okay, now what did they find out? Well, they, out of 10 journeys, 3 trains were late, right? Which means 3 is less than 5, so it means it's not within the critical region. And so what we can conclude is, if it's not in it, we do not reject it, right? So we do not reject H0. Okay, so that's one way of finding out or concluding or working out whether it's significant or not. Now the other method is using the probability method. Okay, so what I can do is now I can use the value of 3. So they said 3 trains were late, right? So what I can find is actually the probability that x is going to be something to 3. Now once again, it's going to be less than or equal to or bigger than or equal to, and once again, it all depends upon H1. H1 once again is bigger than, right? So what we have to do is actually find bigger than or equal to 3. Okay, if H1 with P is less than 0.2, then in this scenario here, we'll go about finding x is less than or equal to 3. So the H1 value is always very, very important. But once again, if we do this, then we can use a calculator or the table to find the probability that x is larger than or equal to 3, which turns out to be 0.322. Now, if I draw the graph, remember, we're trying to find this is a critical region here, right? And this area is 0.05. Meaning 0.322 is going to lie somewhere outside of that region. It's not going to lie within the region, right? Because you need a larger area for 0.322. And so what I can say is, because 0.322 is bigger than 0.05, we do not reject, once again, because it does not lie within the critical region. So as you can see, there's 2 different ways of working out or concluding whether it's significant or not. You can either find the critical region or you can find the probability. You need to be comfortable with both methods, okay? Because they might ask you to use the critical region method, or they might ask you to use the probability method. But after we've done this, then we can write a conclusion in the context of the question. So the question is, May is claiming that the probability of the trains being late has increased, but we found out that it's not increased. We don't reject the original one, so we say the probability of the train being late has not increased. Okay, so this is answering in the context of the question. So those are examples of some one-tailed tests. We're now going to be looking at a two-tailed test. And a two-tailed test is when we have H1 as P is not equal to something. Remember, one-tailed is either less than or bigger than, right? In this case, it just tells us what P is not going to be equal to. Now, there's a couple of differences. The method is very, very similar. This is one or 2 small differences when we're doing this. And that is when we're trying to find the critical region. Before, for a one-tailed test, we either found a critical region where it's like here, or we found a value, if it's less than, then we find a critical region here, right? For a two-tailed test, we actually have to find 2 critical regions above and below the mean value here. So let's call this A and B. So in fact, the critical region is when x is less than or equal to A, or when x is bigger than or equal to B. It's actually 2 different regions. And so when we have our alpha value, which they gave us, right? These areas, because there's two regions now, we actually have to divide the alpha by 2. So it's actually going to be alpha over 2 and alpha over 2. Whereas the one-tailed test, these are just alpha values itself, right? We didn't have to really change it at all. But apart from this, now we just do the same method. We can use the critical region method, or we can use the probability. So let's try this question here. So we have a machine which makes glass balls, and it's observed that 1 in 10 have a hairline crack. Okay, so let's define what x is. So x is the number of hairline cracks. Okay, so the production process is modified and a sample of 20 balls is taken. So it's binomial distribution, n is going to be 20. And 1 in 10 means that the probability of it being cracked will be 0.1, like this. Now, it says one of the balls is cracked. So the experiment or the test statistic they got was x was equal to 1. That's what they got in the experiment. Test at the 10% level of significance, the hypothesis that the proportion of balls has changed as a result of the change in the production process. So remember earlier, to determine H1, we had to look at specific words in the question, right? Whether it rises or falls. In this case, the important word is changed, okay? So they're asking, has the proportion changed? It doesn't state has it increased or decreased, it just means changed. That's why H0 is P is 0.1 and H1 P is not equal to 0.1 because it hasn't specified clearly if it's increased or decreased, it just means has it changed from 0.1. Right, so once we've got H0 to H1 and alpha value is 0.1, we can go about doing the test. So I'm going to once again do both methods so you guys are comfortable with each one. So let's look at the critical region method. So once again, drawing my bell curve. Because it's a two-tailed test, remember I have to label two regions here, A and B. And I can say that the probability of X being less than or equal to A now has to be less than, even though alpha is 0.1, remember to divide it by 2, right? So this is alpha over 2 and alpha over 2. It's going to be less than 0.05 like this. And the second region will be when probability that X is larger than or equal to B would also be less than 0.05 like so. And now we have to find the A and B values both. But finding them is actually the same as the way we found it. You can use a table or the calculator like we did before. And you should get that A is 0 and B is 5. So the critical region would be when X is equal to 0 and X is larger than or equal to 5. Remember it's equal to 0 here because you can't get negative values for this X value. Right, and it says now, how much was the test statistic? Well, X was 1, right? So we can say that 1 is larger than 0 and 1 is less than 5, meaning that it's not in the critical region, right? So that we can conclude that we do not reject H0, okay? So it's not going to be within either of the critical regions. So that's the critical region method. I can use a probability method as well. So we have the probability that X is 1, right? And we're to find is it bigger than or equal to or less than or equal to, and it depends upon our H1, right? But as you can see here, our H1, it does not say bigger than or less than, it's just not equal to, right? So the way we work out whether we should find larger than equal to or less than equal to is actually multiply these two values here. So 20 times 0.1 is going to give us 2. Okay? The reason why we do this is because if we do 20 times 0.1, this actually tells us the mean value. This is useful for later on, but for now, what you can imagine is the mean value, remember, was this value in the middle here, right? So this value here, you can imagine it now to be 2. Because 1 is to the left of the 2, so 1 is going to be somewhere here, right? That means we should be finding less than or equal to 1, like this. That's how we determine whether we should find less than or equal to or bigger than or equal to for a two-tailed test. Just do the n times p value here and then compare it with that mean value. Once we do this, then we just find this probability, and this turns out to be 0.392. We know that 0.392 is bigger than the significance level, which is 0.05, remember half of it. And so once again, we do not reject H0 like here. So the conclusion is the same, it's just different ways of finding out the conclusion. And obviously then you can write a conclusion in the context of the question. So we say the probability of the hairline cracks, in this case, has not increased. Let's try another one here. So we have a standard blood test that is able to diagnose a particular disease with a probability of 0.96. A manufacturer suggests that a cheaper test will have the same probability of success. It conducts a clinical trial with incentivized patients. The new test correctly diagnoses 63 of these patients. Test the manufacturer's claim of the 10% level. Right, first things, X. So X is a statistic and that's a number of, what are we counting? Correct diagnosis, okay? That's what we're counting. And so we have a binomial distribution. The number of patient data was 75, and the probability is the one we assume to be correct, so 0.96 like this. Meaning H0 is P is equal to 0.96. H1, P is, as you can say, they're claiming that the probability of success is the same probability of success. So that means we have to test whether it's different or not. It doesn't say bigger than or less than. We just have to test if it's different. So it's going to be P is not equal to 0.96, meaning that it's going to be a two-tailed test. Right. Our alpha value is 10%, so alpha is going to be 0.1. And the test statistic, number of people who are diagnosed correctly was 63. So that's going to be our X value. It's going to be 63 like this. Right, let's just do both. I'm going to actually use the probability method for this one, okay? So remember, for probability, we have to find the probability that X is something to 63, right? So that's the test statistic. And we have to work out if it's bigger than or less than. And remember, the way we do that is multiply these two values together to get the mean value. So the mean value is going to be 75 times 0.96, which will give us 72 like here. If I was to draw the bell curve, that would mean that this value is 72, the middle value. And because 63 is less than that, it's going to be roughly somewhere here, okay? And so what I would have to do now is find the probability that X is less than or equal to 63, because it's to the left of the mean value, which was 72. And so if we do this, this gets a value of 0.00004. And 0.02344 is less than the significance level, which is 0.05. But remember, we should be dividing this by 2, right? Because it's a two-tailed test. And so therefore we say we do not. We reject H0 because it's going to be within the critical region. The final example I want to do is just a tricky question, or a question that might try and trick the students. So we have the proportion of defective articles in a certain manufacturing process has been found from long experience to P.1. A random sample of 50 articles were taken in order to monitor the production. The number of articles were recorded. So H0, or X-ray, is going to be the number of what we're counting, defective articles. Okay, so X is binomially distributed. They're taking a sample of 50 and they assume that 0.1 to be correct. Using a 5% level of significance, find the critical regions for the two-tailed test of the hypothesis that 1 in 10 articles has been defected. Right, so alpha is going to be 5%, like this here, right? And H0 is going to be P is 0.1, and H1, P is not going to be 0.1, so it's got a two-tailed test, okay? Right, so we've got H0, H1. Now we just have to find the critical region. So I'm going to draw a bell curve just to visualize it a bit better. Like here, so now it's two tails of weapon A and B. So we need to find the probability that X is less than or equal to A is smaller than half of this is going to be 0.025. And probability that X is bigger than or equal to B has to be less than 0.025 as well. And then we can use the table or the calculator to find these values here. Right, normally, in most cases, it's the case that we have to always find less than this significance level here. But if you keep reading the question, it says the probability in each tail should be as near to 2.5 as possible. Okay, so the reason why they say that, or the reason why they're trying to trick you with this, is if I look at the table here, we have 50.1, so we're looking at this column here. So for this first one, less than 0.025, the only one that's less than 0.025 is this one here, right? So in most cases, we'd have to go for this value here. But as you can see in the question, it says it can be as near to 0.25 as possible. And this value here is actually, even though it's bigger than 0.25, it's closer to the value of 0.025 than the 0.0051 here. So what we have to do now is actually say A is actually going to be 1 rather than 0, okay? This is the only difference that because of the question they've asked us. Same thing goes for B. As you can see for B, what we're trying to find is the probability that X, if I was to rearrange this, we get probability that X is less than or equal to B minus 1 has to be larger than 0.975. And so what I'd have to find is find the value which is bigger than 975, which is going to be this one here, right? And so that will be the value that we will have to be using, okay? So we can say that B minus 1 is equal to 9, and so therefore B is 10, okay? And so the critical region will be when X is less than or equal to 1 or when X is bigger than or equal to 10, like so. Okay. So that's the only difference, is when we're finding the initial A value, even though it was less than even though this value is bigger than 0.025, the question itself said it can be as close to 0.025 as possible, so we'd rather choose this one than the value for x is 0. Finally, state the actual significance level of the above test. Well, the actual significance level is actually the values of the critical region. So it's going to be the value of probability that x is less than or equal to 1 plus the probability that x is larger than or equal to 10. Okay, and so it would be this 0.0338 plus 1 minus the probability that x is bigger than 10, which would be 0.9755. And so this will be the actual significance level. Okay, so there's a significance level of 0.5, which is the level that they gave in the question, but the real one will be the value of these two critical regions like this. So that's a quick overview of hypothesis testing. Once again, if you guys have any questions, just leave some comments in the section below.